All right. Well, it's my great pleasure to introduce Marco Fanucchi. Marco graduated with his Bachelor's of Science from Santa Clara University in chemistry, and he actually began his PhD in organic chemistry here at UC Davis. Fortunately for us, he switched over to the Viticulture and Enology program. So Marco, for the last year and a half, has not only been a great colleague, but an exceptional friend. It has been a pleasure to collaborate with him through this program. His foundational knowledge in chemistry has propelled myself and others in critical thinking in the classroom and most importantly, the laboratory. There's no doubt Marco has excelled throughout this program. I think a lot of faculty would second that statement. And he will be an exceptional addition to the Silver Oak Winery as a lab technician for this upcoming harvest. I can't wait to see what Marco does in the wine industry. I know he's succeeded here, and I'm sure he'll succeed as well in the wine industry. So without further ado, Marco, I'll let you take it away.
Thank you so much, Spencer. That was a fantastic introduction. So welcome, everyone. So today I'm going to be focusing on microbiological wine faults and talk about more of a review of anticipated issues in the wine industry and their effects on wine flavor. So the key themes for my discussion today are going to be what defines a fault in wine. Why should wine producers be concerned? We're going to be focusing on 3 faults specifically. So why are these ones going to be a concern in the near future? And those being mousiness, ropiness, and ethylphenols, and how each one of them impacts a different aspect of the over-encompassing term that is flavor, referring to taste, mouthfeel, and aroma. So the first thing is what defines a fault. I'm sure you've heard of faults and taints. So faults are typically categorized as being of microbiological origin, and they are spoilages that occur as a result of metabolisms from yeast or bacteria in a wine fermentation. Volatile sulfur compounds, high concentrations of diacetyl, and of course acetic acid are all examples that I'm sure everyone is very familiar with of faults. Taints, on the other hand, are classified as chemical contaminants due to external sources. So these aren't, with the exception of maybe guaiacols, aren't typically found within a wine fermentation. TCA coming from cork and wood, smoke taint, excessive smoke taint, guaiacols, and glycolytic forms of that coming as a result of smoke. And then cineol from eucalyptus. These are all things that get brought into the winery by some physical means and can affect the flavor of wine. So when we're discussing this, we have some important sensory characteristics that we need to consider. So there's the subjective definition of what constitutes a negative characteristic. And there's also expectations that play into that. So what I might find enjoyable, someone else might not. Similarly, expectations define this. If I were to hand someone a glass of wine that had a high VA and I told them it was wine and they tasted it, they might not find it enjoyable. But if I had handed them that same glass and told them that it was vinegar, that expectation of wine versus vinegar might influence their perception and opinion of the sample. We also have detection and rejection thresholds, which make sensory a little bit more difficult to nail down. There are matrix effects when you are analyzing samples, and we'll talk more about that later. And then you have personal experiences and cultures also influencing what a person might be able to smell. Maybe they're not used to something, or they're very used to something, so they're a little bit less sensitive or more sensitive in that regard. And then, of course, you have genetics playing a huge role as well. Anosmia and hypersensitivity will allow people to either not be able to detect an aroma or be able to detect an aroma or flavor incredibly well, more than the average person. So this histogram right here is actually from a study showing off anosmia towards rotundone, which is the black pepper aroma found in Syrah. So you can see that as the concentration of rotundone is increasing, there are some variations here within the correct number of guesses of identifying the samples. Down here, this is, again, they are guesses. So there are more likely some people who were maybe guessing correctly, even if they didn't know the correct answer. But you can see that it took up until over 2,000 nanograms per liter of rotundone for the majority of the panelists to actually correctly identify that. And only 34 out of 54 were actually able to detect it. So you can see that even at these massive concentrations, not everyone's able to correctly identify rotundone, which can carry over and show effects with other compounds as well. So why should winemakers be concerned? Obviously, wine is the final product, and people have certain expectations of it. So you want to produce a product that people are going to consume, especially when it has such a slow turnover rate like wine. Current trends in viticulture and in winemaking show that higher pHs are becoming more popular. So you can see over the course of time, this study here measured total acidity, pH, and potential alcohol in Languedoc over the course of 40 years. You can see that the pH of the berries at harvest or right before harvest has increased by roughly 0.2 pH units, and the total acidity has dropped quite a bit as well. And then about almost a full gram per liter. The potential alcohol has also increased from about 11% to close to 13%. This also plays some important factors when we're talking about spoilage possibilities. Higher osmotic pressure can lead to stuck fermentations, which can then cause poor fermenters or spoilage characteristics to proliferate. There's also the stylistic influence of higher pH wines. They're typically described as less aggressive and silkier, and being able to go around and use positive words like that might be enticing to the marketing team and a winemaker. So they might want to try and emulate that style. And then we also see a large shift towards organic wine production and natural fermentations, especially with newer wineries, because there is a niche in the market that is looking for that. And unfortunately, there has been some data that showed Pillonnier in 2020 showed that about 69 to 77% of wines that were analyzed over two vintages without any sulfites showed at least one defect. So that's quite a large percentage. But I just want to be very clear up front that the point of this talk isn't to try and deter anyone from making the style of wine that they want. It's just that I'm trying to bring up there are major considerations that you have to take into account if this is the route you so choose. So why should winemakers be concerned about mousiness and ropiness and ethylphenols then? Well, mousiness and ropiness haven't been common in California for the past about, I would say, 4 decades. They have been common in Europe, and they still continue to be, but the industry may not be used to them, and people may not be paying attention to them necessarily. There's also a large gap in the sensory literature, especially concerning ropiness, because of how uncommon it's been. And then Brettanomyces contaminations have been very popular, they're very ubiquitous in a lot of places in California and Europe. But with trends in higher pH wines, it may be that wineries are starting to find their first cases of Brettanomyces contaminations, and they may not be prepared or ready to control that. You also have to consider the fact that operating costs to remedy might be more expensive than prevention. Blending wines, higher cost of analysis, things like that. So for now, I want to talk about mousiness. So what is it on a chemical level? The sense of mousiness, the aroma and flavor is associated with 3 N-heterocyclic bases. You have an acylated pyridine, a non-acylated ethylpyridine, and an acylated pyrroline. So right here, ATHP, ETHP, and APY. So these compounds are capable of being synthesized by Brettanomyces as well as lactic acid bacteria. The precursors for these are most likely amino acids such as lysine and orthine, as well as ethanol and acetaldehyde, and I'll talk a little bit more about that on the next slide. The important thing to know is that these chemicals are not volatile at wine pH. So you won't be able to stand over fermentation and detect this aroma like you would for H2S or something like that. And Tempere in 2019 correlated or collected a lot of data and found that the typical concentrations in spoiled wine ranged quite a lot. So 4.8 to 106 parts per billion or micrograms per liter for ATHP. They noticed maximums of 150 parts per billion for the ethyl pyridine, and then small quantities of APY. APY is actually a byproduct of degradation, more so, and it occurs later in the fermentation than the other two. The other two are synthesized much faster, so typically you're going to see lower concentrations of APY in general. So here is the proposed metabolic pathway for the formation of mousy compounds. You can see that the general heterolytic pathway is going as you would expect up until acetyl-CoA is synthesized. And you can see that over time, the lysine and the orthine are going to cyclize and form the heterocyclic base backbone for these compounds. And any sort of oxidation of ethanol to acetaldehyde would actually allow acetyl-CoA to acylate the heterocycles. The ethyl heterocycle will actually be formed as a result of a enzyme found in Brettanomyces that will actually reduce this, getting rid of this acyl group. So it's not exactly 100%, but this is the most likely pathway that people are speculating. So what is the impact on flavor? Well, typically you're going to see words like rodent urine, grilled food, popcorn, breadcrumbs. But what's interesting is that these compounds can only be detected retronasally, which means that you won't be able to smell them in a wine glass, but you will be able to taste and smell them once it enters your mouth. And this is because as I mentioned earlier, the heterocyclic bases aren't going to be volatile at wine pHs, but once the pH increases as a result of entering the human mouth, there is actually going to be a tautomerization reaction that occurs, and you're leaving this form and forming this amino form, which is volatile and can be detected retronasally. So something very interesting. The detection thresholds vary quite a bit as well. Some people are more sensitive to it. As I mentioned earlier, matrix effects play a major role. So as you can see, there was some orthonasal sensory evaluation in water. And due to the higher pH of water, you would be able to just smell it in the glass. The ethyl tetrahydropyridine, unfortunately, they only did retronasally in wine. So you can see that the concentrations vary quite a bit, which is something you have to consider when analyzing literature for detection thresholds. Interestingly, Tempere also found that the dilution factor between the highest and lowest concentration of APY between 23 panelists exceeded 1,000. So that means the panelist who is the best at detecting APY was able to detect a concentration 1,000 times lower than the person who is having a harder time detecting it. So you can just see that there's a huge amount of variation there. So detecting it and controlling it, detection can be performed qualitatively and quantitatively. So qualitatively, as I mentioned, you need to increase the pH. So you can use what's known as the palm and sniff test or alkaline strips. And that involves simply taking a little bit of wine and placing it either on your hand or on an alkaline strip. The pH of both of those should increase the pH of the wine enough to the point where the compounds become volatile. But if you want to be something a little bit more accurate, because again, if I did the palm and sniff test and I was anosmic to mousiness, I wouldn't be able to detect it unless I verified that with several other people. You can be quantitative about it using gas chromatography with either a mass spectrometer or flame ionization detector. And you can do that with standard methods and olfactory methods as well. So in terms of removing mousy compounds, since they are bases, you can use ion exchange resins. There's some literature that suggests ozone treatments and fortification as well. But this might be unfeasible for wineries, especially not everyone has ion exchange resins. Not everyone wants to produce a fortified wine. So what most likely the remedy is that you are going to take a clean wine and blend it with a contaminated wine just to try and dilute these compounds. And in order to prevent this, it's ideal to maintain a pH below 3.5 and a free SO2 concentration of about 0.8 parts per million. Moving forward, we're going to talk about ropiness now and how it impacts wine mouthfeel. So ropiness is a direct result of exopolysaccharide synthesis by lactic acid bacteria. These are the same structures that are used for biofilms and anchoring to surfaces. What's interesting about it is that it's mediated by a single glucosyl transferase gene, the entire production of exopolysaccharides, and this gene has many variations. Meaning that there is a large variation in chemical structure when it comes to the synthesis of exopolysaccharides. So not all of them will contribute to ropiness. Shorter chained ones in general don't. And it even depends on the organism as well. So Pediococcus parvalis versus Enococcus eni. So Pediococcus parvalis is one of those ones that's probably the most associated with ropiness. But Enococcus also produces exopolysaccharides. The difference between them is that the polysaccharides produced by Enococcus are not chemically able to cause ropiness. So up to this point in time, Enococcus has never been associated with ropiness. The structure is generally just going to be polymerized chains of D beta glucans. The spoiled wines are typically called oily, viscous, and gelatinous. I'll show some pictures, but you could basically grab the wine with your hand or your fingers and stretch it and pull it. It's pretty common in beer due to the higher pHs, and it's common in ciders. Basque Country ciders, they don't add any antimicrobial agents at bottling. To maintain the specific style and characteristic of their ciders. So a lot of this would happen in bottle. But what's nice about ciders is that in terms of its matrix, we can draw some parallels between that and wine. So here's some images of sort of ropey wine. You can see the strands formed in the glass right there as a result of the exopolysaccharides. And you can see, I'm sure you're all familiar with this. I believe it's a picture from 124, the spoon just pulling it right out of the glass. So very unappealing to look at, probably even more unappealing to put in your mouth. Detecting and controlling ropiness might be difficult due to if you're basing it entirely off of morphological features, because like I said, there's a lot of strain differences and genetic differences between bacteria that can actually produce this. So Gindro back in 2001 actually created a method for ropiness detection via PCR, basically being able to single in on the strains that would most likely produce ropiness. You can also detect it with plating. As you can see from this image here, if there is any ropey exopolysaccharide production, it would stick to the loop. Preventing ropiness, pH below 3.6 saw no significant ethyl or exopolysaccharide production in ciders. And then there was a variable impact on total SO2. One study showed that 256 parts per million was sufficient. However, this was at pH 4.5, and that is going to be a much higher pH than you would probably ever have a wine at. And as we know, the amount of free SO2, which is the antimicrobial portion of that, would be more effective at lower pH values. Unfortunately, there's very little sensory data concerning ropiness, and there might be a couple of reasons for that. For one, existing sensory data concerning wine viscosity is not a good parallel to draw to ropiness. Viscosity is typically associated with glycerol and alcohol levels. And as I mentioned, it's like saying Jello is viscous. Is it really? It's more of a solid than anything. Rejection and detection thresholds might potentially be difficult to quantify. Are you able to manipulate the concentration of ethylpolysaccharides in vitro? Are you able to really control which organisms and which structures are going to end up in that sample? Can you dilute one of these samples due to its, the solid structure of it? Potentially not. And can you have something that's slightly ropey? Can you have something, or is there a certain point where it just is ropey? So these are all questions that I couldn't really find answers to. If I ever get my hand on a ropey bottle of wine, I will be doing some at-home experimentation with that. But for now, we're going to talk about ethylphenols. So this is the last spoilage character we'll be talking about today. So typically in wine, we have two different categories of volatile phenols, which are vinyl and ethylphenols. Both are products of enzymatic degradation of hydroxycinnamic acids, which are found in grapes. This can be performed by Brettanomyces, Saccharomyces, and lactic acid bacteria here. They all possess the same esterase, which will cleave the hydroxycinnamic acid here, forming a carboxylic acid moiety at the end. And then all of them also possess the cinnamate decarboxylase, which will decarboxylate here, leaving us with a vinyl phenol. Brettanomyces, however, and Saccharomyces, but the difference between them is that in Saccharomyces, this enzyme right here, this enzyme right here is inhibited by phenolic compounds, whereas for lactic acid bacteria and Brettanomyces, it is not. The only organism that is able to reduce a vinyl phenol to an ethylphenol in wine is going to be Brettanomyces, however. So it's for that reason that you're most likely going to see vinyl phenols in white wine due to the higher acidity and less chance of Brettanomyces being present. And then you will see ethylphenols predominate in red wine. So there are several different kinds of ethylphenols. I'm mostly going to be talking about 4-ethylphenol and 4-ethylguaiacol. These are the most predominant, as you can see by their concentrations, that huge range when it comes to wine. There's also some interesting studies that show that the concentrations of these ethylphenols and their proportions are variable in wines depending on their variety. So Cabernet Sauvignon showed a 10-to-1 ratio of 4EP to 4EG, whereas Bordeaux style blends showed a ratio of 9-to-1, and Pinot Noir actually showed a ratio of 3.5 to 1. And these were all Australian wines. So it's very interesting to see that there's a varietal impact on that. They didn't go too in depth into why they think there is that varietal character. My guess would have to be to do with phenolic concentration, but that's something definitely to look more into in the future. So how do they affect wine aroma? Well, typically you're going to see barnyard, leather, horse, and sweat. At low concentrations, 4-ethylphenol is typically described as medicinal. 4-ethylguaiacol can be spice and cloves, which, at low concentrations, that might be nice. That might impart a desirable flavor to some people. But even at low concentration, ethylphenols have been shown that they can mask fruit flavors in wine. Detection thresholds have been reported for 4-ethylphenol around 440 nanogram or micrograms per liter, and for 4-ethylguaiacol around 33. But what's interesting is that the rejection thresholds of all of these have been reported to be higher than the detection threshold, which implies that even though people are able to detect it, it might not be at a high enough concentration yet that they find it unappealing. Also, there's been some data that shows that isovaleric and isobutyric acids can mask Brett character. So if these are in high concentrations in your wine, it might actually make it more difficult for you to detect these flavors. I want to talk a little bit about some cultural and genetic influence on Brett character detection. I found this study to be very interesting by Schumacher. And they had two different groups of tasters, one from the United States and one from Portugal. And they had a bunch of treated wine that with various ratio, or the same ratio, but various concentrations of the different ethylphenols. And what they found was that the blind control was significantly different from all the other groups. So in this column, this is the mean difference from the control. So they were given a control wine and then they were given another sample and they were asked to say on a scale of 1 to 9 about how different would you say this wine is from the control. So on average, about 3 relatively close, very small difference people detected between the two controls. But between treatment 1, what was interesting is that the American tasters differed significantly in their ability to detect a difference versus the Portuguese consumers. Overall, there was no difference between treatments 1 and 2 in terms of the average values that were used, but none of the other levels had any significant difference between the American and the Portuguese tasters. So what this leads people to believe is that depending on your culture or where you're from, there may be also genetics, there may be some influence on what you're able to detect. So these kind of characteristics you might have heard would be more common in a European wine. Maybe these American consumers are more sensitive to it, or maybe it's because the flavors associated with that treatment aren't something that they really experienced with American wine. So I think there's a lot of really interesting information to be found there. Detecting and controlling ethylphenols. In terms of detecting it, if you have Brettanomyces, you most likely have ethylphenols. So microbial plating can be useful. Of course, you have to be aware of the viable but not inculturable state. So PCR and GCMS are a little bit better when it comes to that. Preventing, similar to the last one, keep a low pH, keep a good enough SO2 level. Colder storage temperatures help inhibit Brettanomyces metabolism, so that can prevent it from spreading and producing ethylphenols. Control and removal, sterile filtration, and blending is a good way to mitigate it. But there has been some recent studies with chitins and chitosins that have been shown to reduce Brett character without impacting overall structure. That leaves some questions about what is overall structure, what are they defining, but it looks like there's going to be some very interesting research moving forward from now. So I don't want to take too much time on the summary. I just want to acknowledge and thank Dr. Hildegard Heyman for mentoring me and working with me on this review. It was a pleasure getting to talk with her, and I learned a lot while doing this. Of course, Dr. Cantu for proctoring and organizing the class. I'd like to thank my colleagues for being there for me over the past year and a half, and I can't wait for all of us to get out there and do great things. And then I'd like to thank the Jastrow Shields, Wine Spectator, John C. Cole Memorial Fund, and the Marchese Antinori for financial support. So if there are any questions, I will take them now. Two questions. Regarding Brett, why do you think there's a low prevalence of vinyl phenols in white wine? Okay, so pH and phenolic structure are going to be, or phenolic composition going to be slightly different. So vinyl phenols, because white wines typically have lower pHs, they're less likely to have a Brettanomyces problem. And since if there's no Brett, you can't form ethylphenols. You're just going to be left with vinyl phenols. But then I would think that there would be some variation in the red wines due to phenolic composition because, or maybe not even phenolic, maybe I misspoke, but I guess hydroxycinnamic acid concentration or the overall structure of that, because depending on if maybe Pinot Noir had a higher amount of the hydroxycinnamic acid moiety that possess the guaiacol form versus the straight up ethylphenol form, you would expect that the concentrations of the final product to be different. So that's a very good question. Yeah, so I guess free SO2 and molecular SO2. Yeah, so I kind of interchanged them there, but yes, you want molecular SO2 more than you want HSO3. If you keep the pH low enough, then you're going to have a higher concentration, but yeah, molecular SO2 is technically the more correct term. So thank you for pointing that out. Oh yeah, do send me the label, Saskia, because I'm very interested. Any other questions?